Welcome to this presentation on polymers. Polymers are very large molecules made by joining together many smaller molecules called monomers. They are important materials because they can be designed to have different properties, such as strength, flexibility, and durability. Definition of polymers and their importance in chemistry. Polymers are large molecules formed by the chemical bonding of many smaller molecules called monomers into long chains. Polymers link organic chemistry structures to real-world materials such as plastics, fibers, rubbers, and biological macromolecules. For example, polyethylene is formed from ethene monomers, and its flexibility and low density make it useful for packaging materials. The size and structure of polymer chains directly influence melting point, tensile strength, and elasticity. Monomers, repeating units, and polymer chains. A monomer is a small molecule capable of joining with others to form a polymer, while a repeating unit is the specific arrangement of atoms that repeats along the polymer chain. Students must be able to identify and draw repeating units from displayed formulas, often using brackets and an N to represent the large number of repeats. For example, in polyethylene, the repeating unit is CH2CH2, derived from the ethene monomer by opening the carbon-carbon double bond. Polymer chains can be linear, branched, or cross-linked, and these structural differences significantly affect material properties. Linear polymers tend to pack closely, leading to higher densities and melting points, while branched polymers are less tightly packed and therefore more flexible. Cross-linking, seen in materials such as vulcanized rubber, restricts chain movement and increases strength and elasticity. Process and conditions of addition polymerization. Addition polymerization involves monomers containing carbon-carbon double bonds, typically alkenes. During the reaction, the pi bond in the C=C double bond breaks, allowing monomers to link together to form a long-chain polymer without producing any byproducts. This feature is essential for exam answers, as addition polymerization contrasts clearly with condensation polymerization. Conditions often include high pressure, elevated temperature, and the presence of a catalyst, depending on the specific polymer being produced. For example, polyethylene can be made under high pressure using a free radical mechanism or under lower pressure using a Ziegler-Natta catalyst. Key addition polymers and their uses. Polyethylene is one of the most widely produced plastics and exists in different forms, such as low-density polyethylene, LDPE, and high-density polyethylene, HDPE. LDPE is flexible and used in plastic bags, while HDPE is stronger and used in containers and pipes. Polypropene has a methyl group on every other carbon atom in the chain, increasing stiffness and making it suitable for ropes and food containers. Polychloroethene, commonly known as PVC, contains chlorine atoms that increase rigidity and chemical resistance, leading to uses in window frames and electrical insulation. PTFE, with fluorine atoms surrounding the carbon chain, is chemically inert and heat-resistant, making it ideal for non-stick coatings and industrial applications. Principles of condensation polymerization reactions. Condensation polymerization differs fundamentally from addition polymerization. In condensation polymerization, monomers with two functional groups react together, forming a polymer and releasing a small molecule such as water or hydrogen chloride. This loss of a small molecule is a defining feature and is frequently tested in exams. Common functional groups involved include hydroxyl, OH, carboxylic acid, COOH, and amine, NH2, groups. Each time a bond forms between monomers, a small molecule is eliminated, leading to stepwise chain growth rather than the rapid chain reaction seen in addition polymerization. Formation and properties of polyesters. Polyesters are an important class of condensation polymers. They are formed by the reaction between a diol and a dicarboxylic acid, with ester links, COO, forming between monomer units and water released as a byproduct. Students must be able to draw the repeating unit of a polyester given the structures of the monomers, using brackets and the correct linkage. A common example is PET, polyethylene terephthalate, widely used in plastic bottles and synthetic fibers. The presence of ester links allows for intermolecular forces such as hydrogen bonding, influencing the strength and melting point of the polymer. Polyesters are generally strong, flexible, and resistant to many chemicals, making them suitable for clothing and packaging. Nylon, proteins, and amide linkages. Polyamides are another major group of condensation polymers. They are formed from reactions between diamines and dicarboxylic acids, producing amide links, CONH, and releasing water. Nylon is a key synthetic polyamide and is valued for its strength, durability, and resistance to wear, leading to applications in textiles, ropes, and engineering components. Polyamides also include natural polymers such as proteins, where amino acids join via peptide bonds, which are chemically the same as amide links. This provides an important link between organic chemistry and biological chemistry within the specification. Addition versus condensation polymers. Addition polymers are formed from unsaturated monomers, typically alkenes, and produce no byproducts, whereas condensation polymers are formed from monomers with two functional groups and release a small molecule such as water. Structurally, addition polymers usually have simple carbon backbones, while condensation polymers contain functional groups within the chain, such as ester or amide links. These differences lead to distinct properties and uses. For example, addition polymers are often chemically inert and used for packaging, while condensation polymers may be stronger and used for fibers. Structure, property relationships in polymers. The physical properties of polymers are determined largely by their molecular structure. Factors such as chain length, branching, and intermolecular forces influence strength, flexibility, and melting behavior. Longer chains generally increase tensile strength, while branching reduces crystallinity and density. Polymers with strong intermolecular forces, such as hydrogen bonding in polyamides, tend to have higher melting points and greater strength. Polymers, waste, and sustainability. Environmental concerns surrounding polymers are increasingly important. Many addition polymers are non-biodegradable, leading to long-term environmental pollution and challenges in waste management. Students must understand issues such as landfill use, microplastics, and the persistence of plastics in ecosystems. Recycling is a key strategy, although it can be limited by contamination and degradation of material properties. Condensation polymers, such as some polyesters, may be hydrolyzed and recycled more effectively. The development of biodegradable polymers and bioplastics represents an application of green chemistry principles. Uses of polymers in modern industry. Polymers are used extensively across modern industry. In packaging, lightweight and chemically inert polymers such as polyethylene are favored. In construction, PVC is used for pipes and window frames due to its durability and resistance to weathering. Synthetic fibers such as nylon and polyester are used in clothing because of their strength and flexibility. Medical applications include polymer-based implants and disposable equipment, highlighting the importance of chemical inertness and sterility. Drawing and interpreting polymer structures. Students must practice converting monomer structures into repeating units, using brackets, correct bonds, and the symbol N. Common errors include forgetting to remove the double bond in addition polymers or misplacing functional groups in condensation polymers. Interpreting unfamiliar polymers requires identifying repeating patterns and recognizing functional groups. Questions may also involve calculating empirical formulas of repeating units or identifying the type of polymerization involved. Using graphs and data in polymer questions. A-level chemistry assessments may include graphs or data related to polymer properties, such as tensile strength versus temperature or degradation over time. Students must be able to interpret trends, describe relationships, and link them to molecular structure. For example, a graph showing increased strength with chain length can be explained by greater intermolecular forces. Connections to other areas of chemistry. Polymers provide valuable synoptic links across the A-level chemistry course. Condensation reactions link to organic synthesis, while intermolecular forces connect to physical chemistry topics such as bonding and structure. Biological polymers such as proteins link polymer chemistry to biochemistry. Environmental discussions connect polymers to energetics, sustainability, and green chemistry. Key takeaways for A-level exams. To succeed in the polymers topic, students should focus on mastering definitions, accurately drawing structures, and clearly explaining polymerization processes. In this topic, we have learned that polymers are large molecules made from monomers. Addition polymers form without releasing small molecules, while condensation polymers release molecules such as water. Understanding polymer structure helps us explain their properties and uses. Thank you for watching.